It's my pleasure. Our first speaker is Dr. Megan Rolf at Kansas State University. She's been there, I wrote this down, since 2016. Interestingly enough, I met Megan when she was a graduate student at the University of Missouri. She actually helped myself and Bob Weber and Dr. Spidell on a bovine respiratory disease project. And so that was her first experience to having to deal with me. But hopefully it wasn't too painful. Clearly she's speaking to my subcommittee, so it can't have been too bad. She didn't turn me down. So before K-State, she was at Oklahoma State for 4 years and got both of her graduate degrees at the University of Missouri. And so Megan's going to talk to us today about some of the work she's doing in methane. And but before she starts, I want to make sure we recognize that our technical breakout sponsor is American Hereford Association. And so at this point, Megan, I'm going to turn it over to you and let you have at it.
All right, thanks, Mark. And I appreciate the invitation to come and share a little bit of what we've been working on. So I assume, based on this morning, we heard a lot about methane, right? But if you happen to show up to this session this afternoon, I'm going to assume that you're not tired of hearing about it yet, because we're going to talk about it just a little bit more. All right, so just a little bit of background. This may be old hat for some of you, but methane is a greenhouse gas that is produced through fermentation in the rumen. So one of the important things related to collection of methane production phenotypes is that a lot of this methane is emitted from the mouth. So we call it enteric methane. And most of it's coming out the front end, not the back. Okay, so the back will only be kind of 1 to 3%. So if we're focused on measuring it, if we could find ways to measure what's coming out the front end, we're going to capture the vast majority of that methane. So why do we care about this as beef producers? First of all, I would argue that we do share some value with the consumer in terms of environmental sustainability, right? In my opinion, nobody's better stewards of the land than beef producers, right? Because that's what we rely on. And so I would argue that we probably want to provide the same human nutritional value of the food that we produce with lower emissions and more environmental sustainability. So if that particular reason isn't very persuasive for you, the second reason that we really care about this is every time that animal belches out some methane, right, this is money that you paid for feed that is now wafting away in the breeze, right? So there's a loss of gross energy of feed when methane is produced as part of this digestive process. They can be anywhere from around 2 to 12%. So I'd imagine that feedlot cattle are probably closer to that 2% for animals that are eating concentrate diets, and those eating high forage diets are probably more of those on the higher end of that spectrum. So this is kind of a trait that, in my opinion, is a bit of a win-win in terms of what consumers might like us to do and things that can positively affect our profitability. So if we look at greenhouse gas emissions, you'll notice that in the US, the methane production in terms of total greenhouse gas emissions is not the largest fraction, right? That's carbon dioxide. However, I think we probably focus on methane a decent bit for 2 reasons. One of those is that it's fairly potent, as they talked about this morning, relative to carbon dioxide. And I think the second reason is probably another one that was highlighted this morning, and that it has a much shorter half-life in the atmosphere. So if we can make reductions in methane production in the short term, we can have a larger impact in terms of kind of warming potential or things of that nature in the shorter term. So if we look at US methane emissions by source, we can see that enteric fermentation is a pretty decent chunk of that. Now, if we break that down a little bit, this particular figure shows, if we focus on that top panel there, greenhouse gas emissions that are coming from a couple of different sources. So if we look at methane on that top line, what we see is that 63 to 80% of total greenhouse gas emissions are going to be due to methane. And this figure is coming from some of the cradle to farm gate life cycle assessments that have been performed by NCBA. So this is probably largely influenced by a number of factors, one of which is the number of animals. So if we think about producing saleable beef product, right, we have to maintain a rather large inventory of cattle, including cows and bulls, in order to make that happen. And not every cow has a calf every year, unfortunately. So we have to maintain that inventory regardless of what our downstream production outputs are. We also have differences due to diet. So that green bar there for methane reflects contributions of the cow-calf sector. So in addition to the numbers of animals that we have to maintain in the cow-calf sector, we also have differences due to diet. So you're going to have more methane produced on a forage diet as compared to a concentrate diet like you might find in a confinement feedlot operation, okay? And because our cow-calf operations are typically going to be grass-based, you see that we have a larger proportion of methane emissions there. And then related to lifespan, cattle spend a large proportion of their lifespan eating those forage-based diets in the cow-calf sector, right? And they spend a year in this phase to hopefully get one saleable calf. So the upside of all of this is that cattle are amazing upcyclers. And the methane production that they have is a direct result of being able to take that forage and produce it into really high quality protein. So the good story out of all of this is that methane intensity, which just like they talked about this morning, we're talking about methane per unit of beef produced, has decreased about 15% from 1990 to 2021. So during that time, beef production grew by about 23% and herd inventory was slightly reduced. And because of that, you see a favorable trend in terms of methane intensity. Now, if you take a slightly dimmer view of that, the other thing that is true in this story is that overall methane production has actually increased over this time period. And that's something that speakers highlighted this morning. So it's about 5% higher in 2021 versus the numbers that we saw in 1990. So even though we've become much better at producing less methane per pound of product, the actual total methane that we've produced in this endeavor has actually increased a little bit. So one of the unfortunate things about the relationship between methane production and some other traits is that more productive animals typically means more methane emissions. And that's why we've seen that absolute methane emission increase a little bit. And there are market signals for bigger animals that maybe eat more because we want animals to be productive, right? So that's part of why you see that trend. However, if you take a look at those regression lines, right, the line is what we would expect to see, but a lot of those dots don't fall exactly on the line, right? So this relationship is not one-to-one, which means that we can take a look at this figure and we can identify animals that gain a lot more than we would expect based on their methane emissions, right? So there are opportunities to identify some of these animals that are sort of, I don't know how to say that, not necessarily producing methane efficiently, but are efficiently producing outputs, right, without having larger methane emissions as a result of that increased output. So those animals exist. The challenge is identifying them and developing tools to be able to select for them. And I would argue, and I'm going to get to this a little bit later, that this whole thing is bigger than methane, right? Methane is important for the environmental sustainability reasons, and methane is important because it's a loss of value to us when we lose that gross energy from the feed. But some of the phenotypes that we would collect in the course of trying to select for traits related to methane can also be utilized for things that might help us get at metabolic rate or things that are more closely related to maintenance efficiency or maintenance energy. And that, I think, is extremely compelling and extremely interesting from a cattle production perspective, especially when we're talking about selection decisions in the cow-calf sector. So the other bad news, if we extend this, is that in order to meet that global methane pledge that they were talking about this morning, which is a 30% reduction in methane emissions by 2030 as compared to 2020, we really need to reduce absolute methane emissions, not sort of improve in intensity, which is what we've been doing. The US RSV and NCBA have set climate neutrality goals by 2040. And at least as far as people that work in this area that are far smarter than me say that we need to actually have methane reductions, right, in order to meet these targets. So we do have an opportunity to make really good impacts within this sector in a variety of different ways. One of those, I think, is going to be genetic selection, just like the speakers were talking about this morning. So in my mind, if we're going to reduce methane emissions from a genetic standpoint, right, we have dietary interventions and all of that really good work that's going on. But if we focus in on the genetics piece, because this is our VIF meeting, I feel like we have two kind of options that we might go about doing this. Ideally, we want to be able to improve without sacrificing the levels of production that we have, or in the absolute worst case, develop tools where we can find an optimum balance between productivity and meeting some of these targets that we may want to meet. So with those two options, the first is to kind of take a modeling approach, right? So estimating methane production with prediction models. So what is the relationship between predicted and measured methane outputs? And if you look at the literature, there's quite a bit of work that's been done in this area. And methane prediction models are pretty good, right? They're largely driven by dry matter intake. And so they will be very closely tied to dry matter intake within that model, but they are fairly predictive from that standpoint. We've done a little bit of work in this, not a ton, but if you have interest, one of our former graduate students who's now at UNL, Drew Laycamp, just recently published a paper of some of the work we've done in this area. But it is a heritable trait, okay? In our study, it was highly heritable, so around 0.6. Take that a little bit with a grain of salt, because dry matter intake in this population was also really highly heritable, towards the higher end of the literature estimates. That's probably why the predicted methane is also fairly high. But of course, these three prediction models that we used, and many of them that you see in the literature, are very highly driven by dry matter intake. In the dairy industry, you can add in milk production and along with dry matter intake and have some additional factors in there. But a lot of what you see that's relevant for beef cattle is going to be focused on dry matter intake. So this approach gives us some sort of information, right? The downside is that when we build these models, we're really modeling for the average, right? So you're not going to be able to find a lot of those outliers because, again, it's a prediction model, not measuring an actual phenotype. And it's limited to what we know about other things, and it's going to be closely tied to those component traits, right? So if it's driven by dry matter intake, finding animals that sort of have a separation between the amount of methane produced for the amount they eat is going to be very difficult with a prediction model. So that's one route. It has some drawbacks. Everything has pluses and minuses, right? So our second option would be to measure methane output directly. So if you look at the literature, the work that's been done in this area, it is a heritable trait. There's quite a few studies that would show that. A lot of those studies have been more confined feeding than grazing. So one of the questions that we have is whether there are major differences between those two different routes for phenotype collection. So we decided to embark upon a quest to measure some methane emissions on grazing beef cows. Because we don't have large numbers of gas flux measurements on grazing beef cows. And so none of this data is really currently put into genetic evaluation systems. So, but I think there's potential for that. There's several options, but they're more limited if you want to target grazing animals, because we have to take the equipment to where the animals are, as opposed to taking the animals to where the equipment is. So you have some more limitations in terms of how to collect those phenotypes. We elected to go with a green feed system made by CLOC. So it is an open circuit gas quantification system, and it looks kind of like this. So the animals are unencumbered. The system's sitting on a trailer. You park it out in the middle of the pasture. The animals choose whether they want to use the system or not, which has pluses and minuses, of course. But basically how it works is the animals can choose to enter this system and stick their head in this little box here. And what's happening is that when they stick their head in there, it's going to drop a little bit of pelleted feed at different intervals, and you can control how much and how often and all of those things. And the idea is to get them to stick their head in there long enough so that we can measure them, what they're exhaling, and then if they happen to burp while they're in there, all the better. And so fans turn on when they do that. Air flows into the system through this tube, comes out the top, And there are sensors that measure the amount of gases in there. When they back out of the system, that fan will continue to run and it will pull air into the system so that you can kind of see what's in the ambient air as well, right? Because the air doesn't not have carbon dioxide in it. So just measuring that isn't enough. We need to be able to measure both, subtract the two, and be able to figure out what gas is being produced by those animals when they're in the system. Ideally, well, so there are a couple of different sensors. All of the systems that I'm aware of have methane and carbon dioxide. You can get optional sensors for hydrogen as well as oxygen. For our system, we do not have the hydrogen, but we do have the other three. So a little bit more on that later. But ideally, this bait entices the animals to go in a couple different times of the day because methane does cycle and has a diurnal pattern that changes throughout the day. So ideally, they visit a couple of times a day. That sometimes happens and sometimes doesn't, but that's one of the things to think about with that type of data. So with these measurements and grazing cattle, we don't have dry matter intake, okay? At least not while they're utilizing the system. You may have it prior to that from a feed intake test or something like that. But the nice thing is that with this system, we can do actual grazing work and take the system out to the cattle. So we now also have sort of dry matter intake, if we had it from some period, and methane production decoupled from any of the component traits that we might utilize to predict it. So that enables us to be able to do something like index development with that information. You have to decide what traits get included. And of course, one question mark, if we're going to include economic values into that is, what is the economic value of lower methane production, right? Without an agreed upon price of carbon, that's in a little bit of flux. But I would argue this is a value-added approach. So with the addition of the carbon dioxide and oxygen fluxes in addition to methane, if we ignore contributions due to nitrogen, we can actually calculate heat production with this little equation down here, okay? So this is the piece that we don't have, but it's actually a very small component of that. So what we've been doing is we have omitted that part and just assumed it is missing and continue to calculate the remainder of the values for heat production. So for us, this is our proxy for metabolic rate, which we think will be related to maintenance energy. You can also estimate forage intake with this data because there are pretty high correlations between methane and carbon dioxide production. So there are some equations to do that. I know they're small, but the equations themselves aren't important for what we're going to talk about today. But to do that, you need to have weight, body weight of those animals, and typically like the weight of a weaned calf or something like that. So one of the questions that we had while embarking on this, this mission was how much data we actually needed to collect on each individual animal and the total number of spot samples that we would need. So most of the research looked at length of trial period and number of spot samples measured for methane. Fewer have looked at carbon dioxide and oxygen. So we wanted to make sure that there weren't any differences for the different fluxes. And then also to kind of get an estimate of how long this was actually going to take, because a lot of what was in the literature would be, there'd be some dairy work, which is a little bit different than a grazing beef operation. And there were beef cows in some of this, but a lot of them were either in confinement or if they were in a grazing situation, it was in a fairly small paddock. And so we knew that for our data collection, a lot of what we would be doing was probably parking the system out in a fairly large range pasture, right, where we don't have the animals confined with the system, which you might expect might have an impact on how many times they would sort of naturally come into that system at any one particular time. But most of these showed that about 40 spot samples was about what you needed. So our first objective was kind of to determine the minimum number of spot samples that we needed to accurately estimate all three of these gas fluxes, as well as that calculated metabolic heat production from an individual grazing beef cow. So for this particular data that we're going to look at first, these were mature Angus beef cows from the K-State purebred unit. And we collected them from the end of May to about the first part of September. We gave them 2 weeks to get used to using the system and kind of coming in to utilize the system. During that time, we take these gates on either side that separate the animals and we put them up so that the animals kind of have free range access to that. So you get lots of multiple animals in there at once and things like that. But that's fine because we throw that data out once they've sort of gotten used to using the system. Then we'll put those gates down and we have a series of panels and things on the side there to kind of reduce airflow, because one of the things that we did with this system is that we put 2 units on a single trailer. If you're going to do nutritional studies, you probably would rather have 2 units on 2 separate trailers, so you could have them in different treatment groups or different pastures, different forage types, things like that. What we really wanted to do is we wanted to maximize our ability to collect larger contemporary groups. So we took both units and put them on a single trailer. So we did want to block airflow between those, and I think we've been pretty successful in doing that. So the first data we're going to look at, we had this system out with 23 animals. Of those 23, 20 of them actually used the system at least one time. So we had a 13% refusal rate. Within this time period, there were 17 animals that used the system quite a bit. So those 17 animals had over 100 spot samples throughout this time period. Some of them had over 200. There's a pretty large difference in the ones that kind of go in and hit that repeatedly. And you have lots of spot samples. And then some others are much more casual users of the system. So we did program our system to have 25 grams dropped every 30 seconds up to 8 times. So that's a little bit different than some of what we saw in the literature. The reason we did that is we wanted to have a larger total number of drops over a shorter time frame to try and keep them in there for as long as possible, because we figured we weren't going to get sort of as frequent visits as some of those other studies might have seen. We allowed 5 visits a day with a minimum of 2 hours in between each visit. So this is our green feed unit. You can see it a little bit better. We've got 2 of them side by side, and then there's a better view of those panels. So we do have some smaller panels at the front, and then we went ahead and put plastic panels all along the sides there, just to help with wind. So at this point in time, we just had generators on there to power the system. We now have generators and solar panels. And then we use this panel system around there just to keep the animals out of the equipment. So we looked at those 3 gas flux phenotypes as well as metabolic heat production calculated here, again, with this nitrogen component missing. So that is assumed to be 0. But it's a very small energy loss to that. So we feel pretty comfortable doing that. And you see quite a bit of studies in the literature that do that as well. So what we did for those 100 visits during this time frame is we did go ahead and truncate that data set at 100 visits. So if they had 200 or any of that, we just considered the first 100 visits. And we started generating averages within increasingly large intervals. So we went by groups of 10. So the first 10 visits, first 20 visits, first 30 visits on to the full 100. We also did the same thing in reverse. So the last 10 visits, the last 20, the last 30. And from there, we would generate the mean using those groups of 10 samples. And then when we did the metabolic heat production calculation, we used those means rather than calculating each individual gas flux and then averaging them. We used averages to calculate it. So 2 different ways you could have gone there. That's what we elected to do. So with those values, we did Pearson and Spearman correlations between kind of that full set of 100 and each of those shortened intervals. And what we saw is that typically there was a fairly large jump in those correlations between 30 and 40 visits, which is pretty consistent with what you saw in the literature. So we wanted to dial that in a little bit more. So we went into that interval and went in intervals of 2. So added 32, 34, 36, and 38 visits within that interval. And so what we were really looking for was every correlation in that interval greater than 0.95. And something similar has been done with a lot of feed intake. We did something similar with water intake. So BIF has done this for a variety of different traits. So that's why we chose that particular threshold. So this is what the data looked like in terms of our averages. Everything was kind of within literature estimates. The one that was a little bit different was our metabolic heat production. It was a little bit higher than what you saw in a lot of the studies in the literature. But I think that's because we had larger mature cows as opposed to a lot of the other studies, which would have had growing animals that would have been a little bit smaller. So a little bit outside of literature ranges, but I think makes sense for the type of animals that we were collecting. So this data shows the correlations for methane. So the blue is going to be Spearman rank correlations. So looking at whether the animals re-ranked, okay. The orange is a Pearson correlation, so your standard correlation. And then those were from the forward direction. The reverse are the yellow and the gray, okay? And so here was our threshold of 0.95. And if you zoom in on this 30 to 40 area here, you see that bigger jump. Here's the data where we dialed that in. So again, there's our threshold of 0.95. Here's 30 and here's 40 in terms of number of visits. And everything's above that line when you get to about 38 visits. So if we look at the exact same thing for carbon dioxide, again, here's our threshold. You start to see things crossing the line at 40 visits between 30 and 40. So we dialed in on that region again. There's our threshold. This one, everything except that reverse Spearman is over that line at 38 visits. For some reason, that reverse Spearman was quite a bit lower in this one. I don't have a good explanation for that, but that was the only one that was like that. So for oxygen, again, here's our 30 and 40, our threshold. We see everything jump to over that line by the time we hit 40. So we dial into that interval a little bit more. Here's our threshold. And we see that everything's over that line by the time we hit 40 samples in that data set. So if we take a look at that heat production, again, here's our threshold. We're hitting those lines between 30 and 40. So again, we'll dial into that region. There's our threshold. And we see that at 36 visits, we've got everything over that line except for that reverse Spearman. It's always that reverse Spearman for whatever reason. Everything except that reverse Spearman is over the line, and it is just really, really close at 36 visits. So the number of spot samples that we sort of saw that exceeded that 0.95 threshold, with the exception of that reverse Spearman in a couple of instances, was between about 38 and 40. So metabolic heat production was a little bit lower, but you need all of this data in order to calculate that anyway. So at a certain point, the 36 doesn't really matter. It's going to be about 40 spot samples, which is very consistent with what we saw in the literature with some of those other production systems. So the other thing we wanted to look at was the number of days, because that varies a little bit in the literature. So for us, it took about 30 plus or minus 9-ish days to hit all of these different targets. So that was quite a bit longer than what we saw in some of those other studies, but I think makes sense when we consider that we didn't have the animals in a small area with this system. It was right out in the middle of a pasture, and they had lots of other places that they could go. So it took us a little bit longer to collect that data. And I think that's fairly logical. But that does lead me to the conclusion that we probably should have in our target protocols a focus on the number of spot samples rather than simply recommending a specific test duration. Because depending on how your setup is, probably will wildly influence the amount of time it takes you to hit that 40 spot sample goal. So if you have interest in looking at this data in a little bit more depth, here's a QR code that'll link you to this paper that we just published maybe a week or two ago, not very long ago. So fairly new one if you want to check that out. So some challenges with this type of work. We know why people haven't done a ton of this, right? Because it is exceedingly difficult. Just to be completely honest with you, it's hard, right? It took quite a bit of time, and it is expensive. And we did have quite a few issues with equipment malfunctions. So I'm hoping that that will improve as we move forward in this work. But that has caused us quite a few delays in the collection of this data. So one of the big questions is, can we implement something like this within the industry? As is, I think some of the challenges that we had would probably exist in that scenario as well. So I think that's something that we'd have to really think pretty carefully about and consider strategies that might help alleviate some of those issues. Another question that we have in terms of industry implementation is we really want to extend these data to more animals. So certainly there's opportunities to do that through pedigree ties, through genomic data, right? Those are all options. But also, you know, when we think about 40 spot samples to get a complete record, okay, that if we set kind of a hard and fast threshold on some of that, that leaves us tossing out a whole heck of a lot of data on a lot of animals. And I would argue there's really no compelling reason to do that. So I think we need to think about strategies on how to use those so-called incomplete records to gain more overall phenotypes and more accuracy in genetic prediction for these types of traits. We also want to, is grazing the same as confinement, right? So if I can go in and I can collect all of my heifers while they're in a dry matter intake test as growing animals, and they would rank exactly the same as they do as mature cows grazing grass, we don't need to be doing this hard thing. We can go do the easier option and collect this data as a part of a dry matter intake test. And that sort of factors into when do we measure these? Can we measure it as growing animals and the rankings stay the same as mature animals? I think those are questions that we still need to answer. So we have continued to collect data past that. So this shows data from 3 different locations and includes all validated visits, as long as each animal had 5 visits or more. Okay, so this includes animals with those so-called incomplete records. And what you see is our values are very similar to what we had before. They're a little bit lower. I think that's because some of the later groups of animals are probably a little bit smaller. So that's probably why you see those differences. We're currently collecting data in a group of about 100 animals. We've got about 60 of them using the system pretty regularly. So we're going to try and really ramp up the collection of this data pretty rapidly, as much as we possibly can. So I gave you all the information on objective 1. So objectives 2 through I'm not sure what will be the future work that we want to undertake, right? So we do want to develop a prototype genetic evaluation. So first, we need to be able to get enough data to fit a univariate model. And then ideally, we want to fit multivariate models to this so that we can figure out what the genetic correlations are, identify important genetic antagonisms, and all those relationships between different traits. QTL analysis would be another big goal that we would have there. So also we want to look into this utilization of incomplete records, because I looked at the correlations of a single visit to the green feed system, and a single visit has a correlation with the values at 100 visits of about 0.5. Okay, that's not low enough where I'm really excited about just tossing that away and pretending that it doesn't exist. So here's what 10 visits look like, and you're around about 0.7, not quite. So even going from 1 to 10 is a pretty big jump. And a correlation of 0.7 is not nothing. So I think there are ways and strategies that we could utilize this data. The exact methodology is something we need to look into more, but that's something that we have interest in doing. And we're working on getting some funding to work on that. And looking at how we might develop indices that include these types of traits. So the biggest acknowledgement I want to give is to Elizabeth Dressler. Elizabeth is my graduate student. She was the Baker Cundiff Award winner last night. She's absolutely fantastic. Elizabeth, are you in here? You want to stand up and wave? So Elizabeth deserves all of the credit because I did absolutely nothing that I presented to you today. Elizabeth did all of it, okay? So this was the royal we presentation. Elizabeth did all the hard work of maintaining the system and collecting all of this data and doing the analysis. So Elizabeth is the person to talk to with questions about this. She's done a fantastic job. I also want to thank Bob Weber and Jenny Borman, who have participated in the project as well. And a huge thank you to the different breeders and producers that have allowed us to come out and collect data, including Shane Work and the purebred unit staff at K-State, Dave Nichols, Matt Perrier, and hopefully we'll have a even bigger list of those folks in the future. So I also want to acknowledge some funding for this project. So the bulk of the funding for this has been provided by the Angus Foundation. They were kind enough to support this work a couple of years ago, and we've been working on collecting more phenotypes throughout this time period. Elizabeth was also supported by the NAAB DOC Graduate Fellowship during a large portion of the work on this project. So a thank you to them as well for supporting her and her work on this project. We also had some feed donated by Countryside Feeds in Seneca, and we appreciate the resources that they have contributed to this as well. So with that, I'm going to stop talking, but I'd be happy to take any questions that you may have.
Any quick questions? I had a question. It was in March and April that the first study was done, right?
May to September, I believe.
May, September.
Yep,
Okay.
yep.
I was wondering if the amount of green grass influenced their frequency of visiting to get your total minimum spot sample ready.
Yeah, that's a good question. I don't think it probably did in that, but that's something we'll look at in some of the other data, because we do hope to collect the data year round. With the understanding that obviously we're not going to be grazing green pastures in January. We're going to try and make sure that the animals are eating mostly hay, high forage diet. And within contemporary group, hopefully that will still allow the animals to be ranked appropriately, so that we can still utilize them sort of with those other records is the idea.